Dask futures are both Dask's simplest interface and its most powerful. You can re-implement any other Dask API using Dask futures, but also very easy to use and very pragmatic in a lot of common situations. In this screencast, we're going to talk about how Dask futures can be used to parallelize a simple, embarrassingly parallel workflow, and also talk a little bit about task dependencies and memory management. So let's take a look at a very simple workflow. Here we have a function inc, which sleeps for 1 second and then does a small amount of work. And we're calling that function inc on a list of inputs. There are 10 inputs in that list, so this should take about 10 seconds. So we want to parallelize this simple workflow. Before we use Dask futures, we're actually going to stop and use the Python standard concurrent futures library. This is the same API as what Dask futures are based off of, but it's included in Python, it's very standard, and it's used pretty widely. It's also my personal favorite library in the standard library. So we've constructed here a thread pool of 4 threads, and we can submit a function to run on one of those threads using the submit method. So here we might submit the increment function to run a number like 10, and we'll get back a future. And we'll get back that future immediately. So it took 600 microseconds, and we get back this future was in a running state. So my increment function, so this is as though I had called inc of 10, is running on some other thread. It only took a second, so probably by now it's finished. And indeed we see, yes, it is finished. That result is sitting on that thread. We can inspect that result by calling the result method. And we see here we got the number 10, or 11, which is 10 plus 1. So this is a very simple way of submitting a function to run on some other thread. And because this happens immediately, we can submit many tasks to run at once, to run in parallel. So we can use that mechanism to parallelize our for loop up here by calling e.submit of inc on x. This now no longer returns a result, it returns a future. Now, this is going to finish very, very quickly. We now want to block until all of our results are finished. So for each of our futures, we're going to call the result method, which will block until that future is done and then return the concrete result. So now, rather than taking 10 seconds, that takes only 3 seconds. Right? So our 4 threads, they process the first 4 inputs, then the second 4 inputs, and then 2 of our threads did some work while the other 2 were a bit lazy. And our results are just exactly the same. Now what's nice about concurrent futures is that it's an API that can be implemented by many different projects. So for example, if we didn't want to use threads, but we wanted to use processes, we could simply swap out for the process pool executor. And now our code would run on separate processes rather than threads. The code would look the same, but have different performance characteristics. Similarly, the Dask client actually satisfies the concurrent futures interface. So you can use it as an executor whenever you would use a thread pool executor or process pool executor. So the same exact code will work with Dask as well, but now we can scale it across a Dask cluster. Here we're using just a laptop with 12 cores, so we use all of those inc calls at once, but this could also be across a larger cluster. So this is very nice. You can start with a local thread pool, play around a little bit, and then only if you need to, you can expand to Dask without much code change. So let's look a little bit more at Dask futures and how they manage dependencies. It's going to be a little bit different from how concurrent futures works, so it's important to get right. So let's make a new future. We're going to submit the arange function to run the number 100, so it's as if I had called numpy.arange 100. Again, that's going to return immediately. But that's finished by now. And so we see that in one of my Dask worker processes, I've now have a numpy ND array sitting in that process's memory. Now it's important to note this numpy array has not been returned locally. It's still sitting remotely, which is very important if I have a lot of these things across many workers. I don't want them all to come back at once. What's also nice is that I can submit another function to run not on a concrete value in my notebook, but actually on another future as well. So this future, again, is pointing to some data in some remote worker's memory. Now we're calling this function sum to run also on that same piece of data, probably in that same worker. So the result is an integer, and if we want to, we can now ask for that small result back. So when we call result, again, we're waiting until the task finishes. So it's finished all of its dependencies, it itself has run, and then we also ask for it to bring the result back into our local process, or in this case, back into the Jupyter Notebook. So this is really nice because I can submit lots of work to run lots of different workers, and that data can stay on those workers. It doesn't have to come back. Only the small pieces that I need to come back do when I call result. So let's dive into that a little bit more with a slightly more real workflow. So here I have a very simple processing pipeline that loads a bit of data. This is actually creating a sizable NumPy array, a few megabytes large, processes that data, making a new array, and then saves that data. So if I run this locally, it'll take a few seconds to run through, and we can parallelize this pretty easily with the Concurrent Futures interface or with Dask Futures. We're going to do that in two ways to highlight memory use and how holding on to memory, how holding on to futures can affect your process's local memory use. So while that's running, let's parallelize this code in one way. Right? We're going to submit these functions to run remotely. And so this X object is now no longer a NumPy array, it's a future. And so if I submit process to run, I'm going to give it that future instead of the concrete result. And Dask will just go ahead and run that task on that result whenever it's ready. I'm also going to call save on the other result. Now, here's something tricky. I actually have to store a future here. Otherwise, Dask will feel free to clean up the result. So we're going to go ahead and grab all of these. We'll talk a little bit more about how it's going to clean up results in a moment. And again, we're going to block until all of those are done. We don't have to do that. If we wanted to, we could just submit it and keep going on with our notebook. But we want to run the time and see how long it takes. Sequentially, it took 35 seconds. Now it took around 37 seconds. So let's run that again, but being a little bit mindful towards memory management. And this is a common fail point. So let's instead submit load on I for I in range 50. Actually, let's increase that maybe to 100. And then we might submit. So the same thing we did in this for loop, but now we're doing it with many lists. And actually, so this pattern is so common that it can be, instead, we're going to use the client.map method. This is exactly the same. We're going to call a process. We're going to map process across the whole list L. So these two lines are the same. Client map is just a little bit easier for some people to write. Okay, so let's run that. So note over here that my memory has increased a bit. So previously I had a few hundred megabytes in memory, but now across all of my workers I've got a couple gigabytes. If I were to increase this to maybe 200, that would increase even further. You can see the memory use increasing over time. This is a little bit concerning. Right? We might soon run out of memory. So the reason for this is that we still have these futures in our local scope. So for as long as we hold on to a Dask future, we may ask for that. At any point, we might say L of 3, give me the result of that result. So Dask feels the responsibility to keep that NumPy array in memory. So for as long as we have a future pointing to a result in Dask's memory, Dask will keep that data around. So the secret to releasing some memory is to delete those lists. If I delete L, we can see that my memory just went down from 3 gigabytes down to about 2. We also saw here in the progress bars that this bar became a little bit more transparent. So while Dask is still aware that there are 200 tasks called load, it has released all but 6 of them. if we go ahead and delete L2, we'll probably also see this process task go so that they're now they're all in memory. If we delete all of these futures, Dask feels that it can now release all of those. Only one left in memory. Now, actually, it's interesting that there are 6 left in memory. Why are there 6 futures still here? It's actually probably these. Interestingly, Jupyter holds on to a lot of futures if they're outputs to a cell. It's a common issue. But this is quite nice. Our memory use is now much, much smaller, down from 3 gigabytes down to 6, just because we deleted some of our intermediate results. This is actually the same process you would have if you were to do this work not without Dask. You would want to delete L1 and L2 after you had computed them. So Dask's memory management looks a lot like normal Python's memory management. If we go ahead and delete L3, probably it'll just delete all of these tasks. So there we go. That's it. There's a bunch more about concurrent futures to learn. You can launch things real time. You can use Python's async and await features. You can have tasks to launch other tasks. You can manage algorithms that evolve the graph as it computes. There's a lot of very fun features to use with concurrent futures. What we've seen here is probably the most common situations. Dask futures are very, very easy to use in embarrassingly parallel situations.